OK, so today we're going to start. We're going to graduate, finally, from axial loading. And the whole class today, is going to be your introduction to torsion. So we are past axial loading. We are sailing along. And today is going to be our first class on torsion. So as we did in axial loading, we're going to start simple. So today I'm going to introduce the basic ideas. And then on Thursday, I'm going to hit you with all the math, right? All the differential relationship and everything that is necessary to solve a general problem in torsion. Okay? But today, we're going to start just with the basic concepts. OK, fair enough. So we want to get to torsion eventually. But in order to get to torsion, to understand things, what I'm going to do is I'm going to do a parallel to what you know. And what you know up to now is axial loading, right? So we're going to start from axial loading, which is what we know. And at this point, you should be very familiar with the basic picture for axial loading. You have some kind of bar of length L. Let's say that it has a width W, and say that it has a depth into the board T. So this is a bar, and this is the way it looks. So it has a certain cross-sectional area A, which of course is TW. OK, so what do we do in axial loading with this bar? We just take it and we extend it in one direction. So we take the bar and we make it longer in one direction, like that. So now the bar looks like that. Same bar. And we loaded it on top to make it longer. And we measure the structural deformation of this bar by this quantity here that we call delta, right? Very familiar at this point. And this thing up here that loads the bar is what we call the normal stress. So what are the characters of our story in axial loading? We have delta, which is the elongation. And this is a structural measure of deformation. This is how much the structure deformed. It elongated by delta from here to here. We know that. Then we have the strain. The strain is defined as, so in this case, the example that I'm going to refer to today, because we want to start simple in torsion. So we're going to relate what we're doing to a simple case of axial loading. So in this case, I have a homogeneous bar. The cross-section is constant. And there is only constant axial load on this thing. So the stress is constant. The cross-section is constant. So in this case, the strain, I can obtain it directly from the structural elongation, because the strain is the increase in length per unit length. So in this case, because the strain is uniform throughout the whole structure, then I can simply obtain it as the elongation divided by the original length. And this is our axial strain. OK, so from axial strain, we know now how to get the stress. So the stress in axial loading is our sigma n. And we obtain it from the axial strain as the axial strain multiplied by actually, let me write this better. Multiplied by, what is this? Young's modulus. So we obtain a normal stress by multiplying the strain by E, and our E is our Young's modulus and this is a material property. right? The Young's modulus is something that's defined at every point. The strain is defined at every point. In this case, happens to be the same everywhere, but it's defined at every point. And the strain, which is defined at every point, is connected to the stress at that point through the material properties at that point, that in axial loading, the only one we need to worry about is the Young's modulus, okay? And then in this case, if I have a sigma n over the cross-section, and the cross-sectional area is A, then my axial force resultant is simply equal to sigma n times A, because sigma n is uniform over the cross-section. So things are easy, and this is what we call our axial force resultant. Axial force resultant. And what we did in axial loading is we took all these things together, and when we combine them together, we get a relationship between the deformation of the structure, which is delta, and the axial force resultant, n. And in this simple case, if you remember, n is simply equal to A over L times E times delta. So the force in the structure is related to the deformation in the structure through this quantity here that you remember is our, stiffness, the stiffness of the structure. And inside the stiffness of the structure, there is geometry, cross-sectional area length, and there is material property, okay? So this was our whole picture for axial loading. And the final destination of today's class is going to try to get to the same point in which we can relate loading to deformation through something that has to do with geometry and material properties for torsion. Okay? All right, so in order to get there, we're going to go through shear. So we're getting from axial loading, passing by shear, we're going to get to torsion. So from axial loading, we're going to get via shear loading. So this is like an intermediate step. So what do I mean by shear loading? Let's start from the same kind of structure. Let's say that I take the same bar, nothing changed, still a nice homogeneous bar, like that. And it still has length L. This is still W. We attach it to the ground right here. And the thickness is still T. So the cross-sectional area is still A. Now I do something completely different. Instead of going over here and forcing it to move up by a certain amount delta, I take this top surface and I make it move parallel to the surface itself. Okay, so here I was moving it up. Now I'm moving that to the side. So the bottom stays put, stuck to the ground. But the top, with respect to where it was, moves. It doesn't go up or down. It only moves parallel to the surface. So that now my bar looks like that. Okay, it's the same bar, but instead of moving it up, I moved it horizontal. This kind of deformation is called shear. I'm shearing this block. Okay? And this thing is still a delta. But in order to remind myself that I'm not going up, I put an S here to remind me that this is a delta in shear. If I wanted to be extra consistent, I should put something here too. Maybe I can put this one as delta due to an axial force N. Okay? I don't want to go back into renaming every single equation that we have. So for now, the axial elongation, we just call it delta. And we just instead put a subscript to this kind of structural deformation. And we call it delta S. So delta S Let's call it the deflection of the structure. And this one is also a structural deformation measure. So you can imagine that if I have something really tall, like imagine that it goes all the way to the basement. Imagine this block going 4th floor to the basement. I take the top and I move it by this much. It's not that much deformation because this thing is so long, it's going to be hard from a distance to even see that I deformed it. Instead, if I take something this short and I move it by this much, you see how much is deformed? So again, in order to get a measure of what the material feels, you need to normalize this deformation to get a strain, right? So what did we do there? We took the delta and we divided by the length. So why don't we do the same? We take the delta. Actually, let me make more room. We take the delta and we divide it by the length. And this one is going to be a measure of deformation per unit length, if you want. And this is called, we're going to call it gamma. And this is another Greek letter, gamma. And this is the shear strain. Shear strain. OK? It's a measure of deformation of the material, which is, again, dimensionless. See? The shear strain is dimensionless, the same as the axial strain. Look, they're look totally the same. So this is our shear strain. Now, you can imagine that this does not just happen because the bar feels like doing that on its own. The bar was totally happy like that. If all of a sudden it starts deforming like that, it's because something is forcing it to deform it. So what is causing the structure to deform that way? If the bar is like this and I want it to shear, the top to shear that way, I need to do something to the surface, right? I need to apply a force to make it go that way. And it cannot be just a force going up, because otherwise it's going to go up. It's going to be something going that way. So what is going that way is also a stress, but it goes along the surface. So the stress that goes along the surface, we give it the symbol tau, another Greek letter, tau. And tau is the shear stress. And is also a force per unit area, the same way as sigma n is a force per unit area. So the units of the shear stress are in force per unit area, which is pascals. Same as this guy. This guy also was in units of pascals. It's a force per unit area, but it's a force per unit area along the area. You see the difference? OK? Pretty straightforward. Now, what we want is we want a relationship like this. We want to know how the stress is related to the strain. You can imagine that the more force per unit area I put here, the more this thing is going to deform, right? So there is a relationship that looks just like that. So the shear force per unit area is proportional to the shear strain that I put in, and the scalar constant between is called G. It's a different constant. It's not the same as E. This G here, this G is called the shear modulus. I cannot write modulus. Modulus. Shear modulus. The same way as the Young's modulus had properties of pascals, because it's a stress multiplied by strain, which is dimensionless. Also, the shear modulus is going to have properties of pascals. OK? So the shear modulus is a material property that connects shear stresses to shear strains. OK? We're going to see 2 classes from now that the shear modulus is connected for isotropic linear elastic material to both the Young's modulus, and the Poisson ratio. There is a connection between these three things. Really, there are only two material properties for isotropic linear elastic materials. And you can choose the Young's modulus and the Poisson ratio, the Young's modulus and the shear modulus. You can choose any two you want. And you can obtain all the other ones as combination of the first two. Okay, but for now, let's just focus on the fact that for a linear isotropic elastic material, shear stresses can be obtained from shear strain through a material properties which is called the shear modulus. Great. I mean, look at this. I want to get there, and I already have 1, 2, 3. Now, I want this now. I want to get here. And after I get here, I want to get here. Okay? So the first thing that we need to figure out is how do we get from the shear stresses to a resultant? Well, as long as I'm just doing shear loading, things are pretty easy. You can say if tau is the shear stress per unit area, then of course if I just multiply, if it's uniform, if I just multiply the shear stress by the area, I'm going to get a force, right? So my force, just to challenge you, is going to be a curly S. And this is the same way as this one was the axial force resultant. This is, guess what, is the shear force resultant. Right? Shear force resultant. We have no imagination. We are engineers. Like we just go along. If that's the shear strain, this is the shear stress, this is going to be our shear force resultant. And in this case, where again everything is homogeneous, then it's as simple as that. Okay? So remember that this is not our destination. Our destination is not to learn about shear loading of a slab of material. Our destination is torsion. So this is kind of like a passing along. We're passing along into shear, but we're really heading on to torsion. So the shear force resultant, for now, you just bank it in your brain, because this shear force resultant is going to pop up again when we do banding. When we do banding, we're going to go back to this concept, and we're going to look at the shear force resultant in banding. Because banding, if you think about it, is when you banding is when you take a structure and you load it orthogonal to the length of the structure. Okay, so we know that we're going to get back here at some point. But for now, let's say that this is just our intermediate step. Does this move of its own? Am I imagining it that keeps going up? It's like gremlins or something. Okay, so we're going through shear loading, and our destination is going to be torsion. So how do we get to torsion from that? Well, it's kind of simple, actually. So we're going to have to torsion. And today, because we want to make our life simple, we're going to do torsion of a thin walled tube. Okay. So how do we get there? Okay. Imagine that this is my bar, right? Now, what was I doing? I was attaching the bottom, and on the top, I was shearing it that way. Now imagine that I take this bar and I make it very, very thin. So T is very small. And I make W big enough, very large. I make it W much bigger than T. So take something like that and take T much less than W. And then you wrap around into a tube. And so now I take this thing and I wrap it around like that. See? I made a tube. It is the same kind of guy as this one. and I wrap it. And then I do to this sheet the same thing that I was doing to the bar. So I have this other handy-dandy demonstration tool, which is a piece of the insulation in my pipes in the basement. I went there last night, and I zip, 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 cut a foot of it out of my heat pipes. It's just foam. And my husband is going to find out, get mad at me because I'm wasting heat. Money here is going out from 1 foot of my basement pipes to increase global warming, right? So, but now we have a demonstration of what I want to show you, right? So this used to be straight, imagine, like this, and I wrapped it into a tube, right? So when I was shearing it like this, if I want to do the same thing to the tube, if I was shearing it along the surface, what happens to the tube is that it used to be straight like this. And if I start shearing the top, see what happens? Right? It twists. It goes in torsion. So I go from this kind of concept of shearing the top of a slab of material to wrapping the slab around and then shearing this side. And the result of it is that the tube gets twisted around. You see the line? It used to be straight. It's not straight anymore. Actually, it wraps around in a straight edge along the pipe. So when we take our sheet and we wrap it around, we get something that looks like this before we deform it. So it's attached to the bottom, and this is where the seam was. Imagine that I attach it, I glue it together, but that's where the seam was, like that, right? This is our tube. And this is still our thickness T, same as before. And now the tube is going to have a certain radius. Let's say that the radius of this tube is R. So if the thickness of the sheet was much smaller than the length of the sheet, then it's also true that the thickness of the tube is much less than the radius of the tube. This is called a thin wall tube, or a thin-walled shaft. So in torsion, the elements that we're dealing with, they're not bars anymore. Just because they are loaded in torsion, we call them shafts. Okay, so these are shafts. And this one that is created by taking a thin wall, a thin sheet and wrapping it is called a thin wall shaft. Okay, so what happens when I put shear on top of this shaft? What happens is that now the shaft looks like this. So it started like this, and this was the line where the seam was, like there. But now, you saw what happens when I twist my insulation tube. This seam gets moved around. It becomes like that, right? That's what it looks like when I twist it. And it becomes like that because to the top of this surface here, I'm applying my shear stresses. So these are still my shear stresses tau. It's just that I have wrapped it around, all around the circle. And so it looks like that. Okay? Fair enough. Now, what is this angle here? From the vertical to the line that goes to the seam right now. Who is this angle here? What did we call it? We didn't call it. That's a very bad moment of amnesia on my part. I should have called this something. See this angle here? This, I can call it gamma. Why can I call it gamma? Because in 201, the deformations are small. So the way I define the strains, you see, is this length divided by this length. The ratio would generally be the tangent of this angle, right? if gamma was big. But because delta S is small, and when I say small, it means small compared to the length there, then this one is about equal to the shear angle. Okay? So gamma, which is defined as delta over the length, approximately is also equal to actually the angle, of course, in radians. Gamma here. So just because I wrap it around, that doesn't change things. So this angle here is still gamma, right? Okay? Okay. And this distance here that I traveled is still delta S. It just happens to be around the band. Okay? But it's still delta S. Now I can define another angle. If I look from the center of the circle, from where I was to how much I rotated the top, you see the top has rotated? How much the top is rotated, this angle here is a very important angle. And this angle here is called phi. And phi is our main character for deformation in torsion. So let's give it a name. Phi is called the angle of twist. And this is the measure of structural deformation in torsion. This is the equivalent to that delta in tension. Okay? You see the two guys? I'm going to try to make that board look just like this board here. Okay? So phi, my angle of twist, is my structural deformation. Now, we already said that my shear strain, gamma, is simply delta S over L. I'm not going to change that. So gamma, which is my shear strain, is delta S over L. That's still my shear strain in the walls of this tube. Just because I wrapped it around didn't change that. Okay. Now I'm going to use the fact that I can obtain delta S either by multiplying this angle by the radius, or I can obtain it by multiplying delta by L, right? So delta S, I can also write it as phi times R. That's also another way of obtaining delta S, just angle times the radius. Good?
Wait, that's delta S, or is that?
This thing is delta S, and I still need to divide by L. I'm not dropping the L. Okay? So another way of obtaining the shear angle in the wall is by taking the angle of twist and then multiplying it by R over L. Okay? And actually, let me put this L under the phi. The reason that I want to put the L under the phi is that this guy here actually also has a name. And my phi over L is called the twist rate. And it's an important concept, because if you think about it, it tells you how much I'm twisting per unit length, right? So it has its own name. So let's write it like that. And actually, I want you to notice that in this definition of gamma, let's put a little r here, because this is the gamma at this particular radius. Because the wall was thin, what I'm saying is that every single spot inside this tube is approximately a radius r. I drew it a little thicker because I need space to draw my tau. But in your mind, you have to imagine that this is a wall that is very, very thin compared to the radius. So every point on this top surface is approximately at the same radius r. Okay? So notice that what I obtain in this equation is gamma at this radius r. And the r gets into the definition of gamma. You see that? We're going to use it on Thursday. when we're going to see what happens if the shaft, instead of being just a little thin ring, is solid. Okay? But for now, let's just keep this in mind. Okay, so we're getting there. And what do we do next? We do the shear stress. So the shear stress tau, we already know how to obtain tau. There it is. I just need to multiply gamma by g. So tau is simply equal to gamma multiplied by g. And so that's going to be equal to gamma that multiplies phi over L, our twist rate, times r. And you see also the tau, in the definition of tau, in this structure here, we get the tau at a certain radius. Let's put a little r down here, just to remind ourselves that this is tau that we obtain for a cylindrical wall of radius r. There is an r in there.
Are you supposed to have the tau there?
What?
You are not the tau, I'm sorry, was it gamma? You have gamma times.
Oh, sorry, I'm supposed to have g here. Thank you so much for calling me on that. Sorry, that's g. Sorry. Okay? G gamma. Very different. Okay? Okay. So this is still my shear strain in the wall. And this is now my shear stress. Okay, so now we need, in order to get here, to this eventually, I need to get this one. What is the resultant of all these shear stresses? So the next thing that we need to do is get a resultant. That's our next step, okay? We're good? Do you guys have any questions? You're getting ready to eat your Twizzler? We're getting there. So we're getting ready to get there because we're going to do a little detour into sign conventions. You know, like the sign convention in axial loading were pretty clear, right? Axial loading, the sign convention. The elongation was positive if things get longer. The stress is positive if it pulls on the bar. The strain is positive if things elongate and stuff like that. We need something similar to that in torsion. Now, torsion is a little harder to see because things do not get longer visibly. They twist around. If you take a tube and you twist around, it still looks like a tube, except if you cheat and you put a thing in it, right? But there are conventions for sign. So
are we resulting, we're saving that for later? Or?
Yes, because in order to do the resultant, first I need to figure out what sign the resultant is going to have and things like that. I did not even tell you what the resultant is going to be yet. In order to get there, I want to make sure that we know how to deal with the angle of twist, positive or negative, the shear stress, positive or negative. I need something there. So my sign conventions are very simple. So the sign convention is that the right-hand rule rules torsion. Okay, so the right-hand rule means you take your hand. Oh, God, I cannot draw this hand. I'm going to do like that, kind of. It's a very ugly hand. Okay, pretty ugly. Okay, so you take your thumb, and your right-hand rules tell you what rotations, what is the axis of your rotations, the axis of your torques, because we're going to get into torques. And essentially, the way your fingers point gives you the direction, okay? So the thumb, if you rotate this way, the thumb gives you the positive direction. So positive for everything that has to do with torsion is going to be that your thumbs are out. Thumbs out instead of thumbs up. Thumbs out of the surface. The same way in which in axial loading, a positive elongation is out from the surface. A positive stress is out of the surface. And if you remember, the axial force resultant was out of the surface. That was our positive sign for axial loading, right? It's going to be the same sign in torsion, but the way you define the out is with your thumb. So if you look at your angle of twist, an angle of twist is positive if something that had straight line, once it's deformed, looks like that. So this is a positive angle of twist. Why? Because I went here, and if I draw the axis of this angle of twist, I had to turn it that way. Look at the way my thumb points. Out. You see? And now you can open your Twizzlers. Open your Twizzlers. I'm going to open one too. Open your Twizzlers and also look at one of the black guys, the black licorice stuff. OK, so we open our Twizzler. And somebody made it. Somebody made the shape of the Twizzler like that. It didn't start like that. Actually, I can't open the Twizzler, can I? I have chalk everywhere. Did you eat already your Twizzlers? Is that why you don't have it?
No, I never.
Confess. OK. Now imagine that somebody made the Twizzlers, right? They started off straight. So untwist them and make them straight. And then let them go and see the way they go. So you see how they rotate? Put your fingers in the direction in which they rotate and tell me what angle of twist do the Twizzlers have, positive or negative? Which way is your thumb going? So what's the sign of the angle of twist of Twizzlers? Negative. Twizzlers have negative angle of twist. Notice that I cannot just change that if I turn it upside down. Right? If I turn it upside down, I make it straight, and I see which way it goes, it still goes in. The angle of twist tells you how much is the deformation with respect to the straight configuration. And it doesn't depend on how you orient the structure, the same way as if you take a bar and you make it longer. It's not like if you turn it upside down, now it's shorter. Longer is longer, right? Somehow twist is harder to see, but it's the same thing. If something was straight, and now it's twisted, it doesn't matter if you look at it like this, or like this. The twist is always either in or out, right? If you look at your black guys before, you can eat the Twizzler now. If you look at your black guys, look at the way the twist is. If you make it straight, and then you let go, which way is it twisting? Is the black positive or negative twist? Positive, because when you let go, you see it twists that way. So the twist is out. OK? So positive or negative angle of twist, it only has to do with from where it was straight to when it deforms. And I describe the deformation, and I go with my fingers just along the deformation. I look at my thumb. If my thumb is in, the angle of twist is negative. If my thumb goes out, the angle of twist is positive. Clear enough? It has nothing to do with axis. Coordinate axis, nothing. It's a measure of the structural deformation.
So if you hold like the top of the Twizzler and then do that and it reverses it, is that still out? Or is that...
The Twizzler, always, if you look at your thumb, the angle of twist the twist always goes in. So if I hold the bottom, I untwist and I see what happens. It goes that way, like that. My thumb is in. If I hold the top and I untwist the bottom, like that, and if I see the way it goes when it deforms that way, still in.
So it's relative to where it's fixed.
It's relative to the way it was before it deformed.
Okay.
So if I imagine that this Twizzler, before it was manufactured and set in this shape, used to be straight. Then somebody went in and twisted it. And I ask myself, the angle of twist that they gave to this Twizzler, is it a positive angle of twist or negative? Then I see the way it's twisted, and I see if my thumbs go in or out, my right hand thumb, not my left hand, because that's opposite. My right hand, does it go in or out? It twists that way. It goes in is a negative phi.
But relative to that picture and the Twizzler, if you were to hold the top, then you would need The opposite sign. Like you're right
Start straight. Start straight. I hold the top.
Okay.
And it's like towards the person.
Okay.
Yeah, so if I hold the top, then the surface I'm looking at is this surface. The surface normal is out that way, right? You got me? Okay, I'll stop then. All right? We good? Excellent. So I cannot eat the Twizzler because I have celiac sprue, and they put flour in Twizzlers. Can you imagine? An Italian that cannot eat any gluten. It's really disaster. Okay, so positive angle of twist. The stresses, same thing. So if this is my stress, if it goes around that way, counterclockwise, so my counterclockwise stress, like that, this is a tau is positive. Okay, same thing. If the tau goes around, look at the way the tau goes, it tells you which way is positive. The same way as when you do uniaxial loading. Remember that in uniaxial loading, a positive stress always comes out on both sides, right? Because the material needs to be in equilibrium, right? So sigma n positive comes out from the surface both ways. Same thing for the shear here. A positive shear on the top looks like this. Of course, needs to be balanced by what happens on the bottom. So on the bottom, if the top does that, for this not to start spinning around, on the bottom, something must be going on the opposite way, right? So on the bottom, the direction of the tau is going to be looking like that. And notice that when I draw it like that, my thumb still comes out of the surface at the bottom, you see? My thumb always comes out. I do a double arrow to indicate the axis of the twist. Okay? Out. Out. Okay? If you get this in your mind, you're like totally close to the destination of torsion. Okay? Positive sign convention. Okay. Now we're going to leave this here because we still need one more guy here, the equivalent of n. So let's go back to our task here. That is, we want to find the resultant of all this stuff.